right, good morning, everyone. I don't have an announcement slide, but really the only announcement is that I will post the Achieve homework today, and I will post the midterm key today. Sorry that those are both delayed, but they will get done today, so you can start working on the Achieve and reviewing the midterm questions. But the Achieve won't be due until after spring break, so you'll have an extra week to work on it. My office hour tomorrow is at 2, so I have to change it again because faculty love to schedule meetings during dead hour, so I have to always change my dead hour office hour to be 2 p.m. So it'll be 2 tomorrow. We still have recitation on Friday, and then our class on Friday, of course. And then I posted an announcement. I'll talk more about this on Friday. But there's a really great research-focused opportunity if you all are maybe interested in doing research in the future, and if you have questions about what it even means to do research, I'm happy to help you out with that. But there's a really nice program that provides stipend and tuition funds and things like that, and I posted an announcement about it. So you can read through that announcement. I'll talk more about that on Friday, but keep that in mind if you're interested. Even if you're pre-med or pre-dent, you have the option, or you might choose to do research through those programs in the future, or do research in undergrad, so that program can still be helpful for you. But especially if you are considering the PhD route in chemistry, biology, some STEM field, this program will be definitely really wonderful for you. So take a look at that. I'll talk more about it on Friday. Okay, so let's get right into and continue what we were discussing on Wednesday. So we have been talking about K, the reaction quotient or the reaction constant, which is calculated through this general equation here. We have concentration of products over concentration of reactants for any reaction. And so if K, that value is equal to 1, that must mean that at equilibrium, reactants concentration is equal to product concentration. If K is greater than 1, that must mean that the numerator is greater than the denominator, so there are more products at equilibrium than there are reactants. And if K is less than 1, then the opposite is true. The denominator is larger than the numerator, so there are more reactants than products. Okay, so we have been discussing K in terms of concentration of reactants, but if we have a gaseous equilibrium reaction, we can also calculate Kp, which is a ratio of the partial pressures of each component. So we discussed partial pressures last term, but if you have a container of multiple gases, the total pressure of all gases is the sum of each individual gas partial pressure. So for example, in this equilibrium equation, if we had all of those molecules present in a container, there will be a pressure of carbon monoxide, CO, only. That would be the partial pressure of CO. There's a partial pressure of O2, a partial pressure of CO2, and adding all of those together gives you the total pressure inside that container. So we can also calculate partial pressure using the ideal gas law, so we're assuming ideal gas behavior. But for gaseous equilibrium reactions, K can be expressed in terms of each component's partial pressure. So if you are calculating K without a subscript, just K, that is referring to the concentration version of K. This can also be represented as Kc, C for concentration, or Keq, Eq for equilibrium. We have that on a previous slide. But if you are specifically calculating for Kp, that is the K in terms of partial pressures. So this is, the C is concentration. And then the P over here refers to pressure. So Kc is the same thing that we've been talking about. concentration of products, CO2, raised to the power of its coefficient divided by concentration of reactants, raised to the power of their coefficients. So this is what we discussed already. You should be able to generate this fraction here, concentration of product over reactant. And then Kp, we still have product over reactant, but now instead of concentration, we are representing their partial pressures. So Kp is pressure, partial pressure of the product, CO2, raised to the power of its coefficient. So partial pressure of CO2 squared and then reactants in the denominator.
Why is O2 squared?
It shouldn't be. Thank you. So same process of putting this together, except instead of concentration, we're representing partial pressures. So these two values are different. Kc is not directly equal to Kp because pressures of these components will have different values than concentrations, but we can convert between them and we'll go through, this is like 7 or 8 steps on the next slide to show how we get the equation to relate Kp and Kc. All right, so for this equation, we're talking about general reactants and products here. Kp is pressure of products raised to power of coefficient divided by partial pressure of reactants, again raised to power of coefficient. So this, I'm just writing the Kp equation, same thing, same process as the previous slide. And then with all this space, we'll show how we convert between Kp and Kc. Okay, so we are going to use PV equals nRT, ideal gas law, so we are assuming ideal gas behavior. And Kc is concentration, the ratio of concentrations. Concentration is amount per volume, or mole per volume, or N over V. So we're going to rearrange PV equals nRT to solve for concentration, which will be N, which is moles, over V, which is volume. So first solve for moles over volume, which is molarity. So rearranging PV equals nRT, N over V equals pressure over R times temperature. So using that relationship, again assuming ideal gas behavior, we will write Kc, so concentration, but instead of putting in moles per liter for each reactant and product, we'll put in partial pressure over R times temperature, because that is equal to moles, the molarity. So Kc is equal to, for each molecule in the overall reaction, we've got partial pressure of C divided by R times temperature raised to the power of the coefficient lowercase c. And then we'll do that for each other molecule in that reaction equation. So D for the other product and then A and B for reactants. Now, we're talking about a reaction at equilibrium at a given temperature. So for each of these fractions, the temperature is going to be the same because the system is at equilibrium at a certain temperature. So T is the same for each of these small fractions. And then R is the gas constant, so that's not changing. We're going to now remove R and T from each of these fractions and multiply it by the pressures. Pressures of each one will be different because we're talking about the pressure of individual components. So we're just rearranging the equation here, where now we have pressure of each product divided by pressure of each reactant. All of these need to be raised to their exponent. Times 1 over RT. Actually, before we simplify further, we've got 1 over RT in the numerator raised to C plus D. So when we're combining, we still have 1 over RT raised to the power of C, 1 over RT raised to the power of D. We multiply that together, we've got 1 over RT raised to the power of C plus D. That's the exponents. Now we'll do the same thing in the numerator. I mean the denominator. So again, just rearranging to get pressures together, and then RT, which does not change per component. Pressure is unique to each component. RT is the same for all components. Get that separated. But now that we have 1 over RT in the numerator and denominator, we can combine these. And the exponent, when we combine them, will be C plus D minus A plus B. Like minus A minus B. So this is equal to now, more rearranging. All pressures look the same. But now we've got 1 over RT to the power of C plus D minus A plus B. Questions so far? Okay, we will simplify this even further. This fraction here is the same fraction as what we have for Kp up there. So instead of writing all 4 of these partial pressures, we can say this is Kp. Oops. And then this exponent, C plus D minus A plus B, is the change in coefficients from the reactant side, or the product side to the reactant side. So we add together the coefficients of the products, and then subtract the sum of the coefficients of the reactants. Or in other words, this is the change in moles of reactants to products. So we're going to simplify this as delta N, which is moles of products minus moles of reactants. And we can determine that with the coefficients. So with that simplification, Kc, I'm working on the bottom left now, is equal to Kp times 1 over RT to the power of delta N. So if you are given an equation, you're given Kp, then you can calculate Kc by just plugging in Kp, raising 1 over RT to the power of delta N, and then you've got Kc. We can also rearrange this to have Kp on the left side. So if we divide by 1 over RT to this exponent on both sides, we'll have Kp is equal to Kc times RT to the power of delta N. So the fraction is inverted, but we still have delta N as the exponent, and then Kc is getting multiplied by RT to the exponent. So both of these are useful depending on what you're provided to convert between, and if you have one, you can always generate the other just by rearranging. But to convert between Kc and Kp, you've got these two equations that you can use. And we've, again, related them with the ideal gas law. Now, when we're talking about concentrations, they are in terms of moles per liter. So that means our R value must be the R value that contains the liter in its units. So that is R equals 0.0821 liters times atmospheres divided by mole times Kelvin. So for these equations, we're using this R value. The other R value doesn't have liters times atmospheres, it has joules here. And we use that other R value when we're talking about energies. We're not talking about energy at all here. So you've got this R value. All right, I'll leave this slide up, but you're going to work on this problem here. So we have a real reaction. SOCl2 forms SO2 and Cl2. You've got Kp, and your questions are to write the Kp equation, so partial pressures, where they go in the fraction, and then calculate Kc. So I'll get this started. But I'll put the previous slide up in case you still need it. Yeah, when you're given. Plug in our temperature, which is 500. Yeah, and then there's trouble, and then. Yeah, but that's gonna be one over. So the coefficients. So you add together the coefficients of the product and then subtract the coefficient of the reactant. Yeah. No, so this is just one molecule and then the coefficient is one. Yeah.
I get this answer to this. I have to calculate it. Because we can use this.
Well, that's actually not the equation that you're using. This is just what the expression would be. So like, this is like we wrote partial pressure So the first one, you got the one right, so you get the point. But when I explain it, the first one will be different. It's not the one that you selected, but I'll explain why. But you're gonna get the point for today for the one. All right, 30 seconds. Okay, I'm gonna close it. So we've got this reaction equation, we have Kp, we have the temperature, and we're looking to first write the Kp equation. So that is partial pressure of products, SO2 and Cl2, divided by reactants, partial pressure of SOCl2. So just remember, if you're writing the equation for Kp, you need pressures, partial pressures. Kc or Keq or just plain old K is the concentrations. To calculate Kc, we need the equation from the last slide that shows the relationship between Kp and Kc, where we're solving for Kc. So we can plug in Kp, we have the gas constant, we have temperature, and we can find delta N. So we will use Kc equals Kp times 1 over RT to the power of delta N. We are provided Kp 1.23 times 10 to the negative 6. R is 0.0821. Temperature is provided as 500 Kelvin. Now remember, our units, gas constant units, are liters times atmosphere divided by mole times Kelvin. So you need to have temperature in Kelvin. If you're provided Celsius or Fahrenheit, you're going to have to do a conversion. So keep that in mind. And then delta N, we're looking at coefficients of the products, add them together, subtract coefficient of reactants. So we have two products here, each have a coefficient of 1, so add that together, we have 2. And then we have one reactant with a coefficient of 1. So we're doing 2 minus 1, so 1. So plugging all of that into the calculator, we have 3.00 times 10 to the negative 8. Now by convention, we don't include units for K. For Kp or Kc, we leave units out. So in this equation here, if we were to keep in pressure units, we would have units of ATM. But if we had another reaction with 2 reactants, all of the units would cancel out. Or if we had more reactants than products, then we'd have ATM in the denominator. So the units, if we followed our rules for units, would change per reaction. By convention, we just leave units out for K. That goes for Kp and Kc. So no units for K. All right, questions on what we've got so far? Yeah.
So instead, I messed up because I kind of did like 2, like for the delta N, I did 2 plus 2 because it had like the 2 oxygen, 2 chlorines.
Okay.
But I didn't know it was, so it's the element, like how many?
Yeah, it's the coefficient per molecule or element. So like coefficients right here are not drawn in because they're all 1. But all of these are 1. So on the product side, we have 2, reactant side 1. We're just adding them together. And then you do products minus reactants, so 2 minus 1. Okay, so far we've talked about what K is, how to formulate the equation for K, what it tells us. Oh, by the way, does this reaction lie to the left or right? Talk to other people around you. All right, so this value here, 3.00 times 10 to the negative 8, we convert that out of scientific notation, it's 0.00000003. So a very small number. So does that mean in this fraction, the pressure of the product or pressure of reactants is larger? The reactants, yeah. The reactants is larger. That must be larger than the numerator to get a small number. So if pressure of or concentration of products is or reactants is larger than products, that means we have more of what's on the left side of the equation than what's on the right side. So we say this lies to the left. So small k reaction lies to the left, the reactant side. Large K, it lies to the right. Okay, so now we're going to, in the next section, use these equilibrium expressions. We're just going to calculate K first. That will be pretty straightforward. And then manipulate K values for changes to reactions. We'll get to that after this first example. So here we have a reaction, two products, two reactants. We have a certain temperature, which is not specified, which is fine. You are calculating Kc. So you have concentration values at equilibrium. You should be able to put together the equation to calculate K, and that's all you're doing for this slide. Oops. Or actually, what we do, just plug in the numbers that we're given. Yeah.
No, I don't care.
Oh, wait, hold on. Yeah, I got it. But One more minute.
Oh, is this for? She doesn't know. I figured it out. Yeah, yeah.
All right, 20 seconds, I'll close it.
Yeah, the products are either CO and CO. And the reactants are CO2. Yeah.
Okay, closing it here. All right, so for this equation or for this problem, we need to write out the Kc expression. Remember, it's products over reactants. So CO2 times concentration of H2. Now, these are all in the gas phase, but gases can have a concentration, and that's what's provided to us here. So CO2 over H2, times H2, divided by CO times H2O. So we're looking for Kc, K in terms of concentration. We're provided concentration values, so we don't need to do anything with Kp. That's not needed for this equation. So now that we have the Kc expression, we don't have any exponents because all coefficients in the reaction equation are 1. Now we just plug in values. So CO2 concentration is 0.150. H2 concentration 0.300. CO 0.06. And then H2O 0.120. Another thing that I heard come up is in the past, if we had H2O as a liquid, we keep it out of the K equation, but that's only when its phase is liquid or solid. But it's a gas here, so it stays included. Kc expressions include gases and aqueous materials, not liquids and not solids. But here it's a gas, so we include it. So then if we if we simplify this fraction, we have Kc is equal to 6.25. So now, does this reaction lie to the right or to the left?
To the right.
To the right, to the product side. We have K is greater than 1. Concentration of products is greater than concentration of reactants. So this reaction lies to the product side, which is the right side of the reaction equation. So lies to the right. Questions here? Okay, now the next slide. Well, let's note right here we have carbon monoxide and water forming carbon dioxide and hydrogen. Next slide we have carbon dioxide and hydrogen forming carbon monoxide and water. So we're working with the reverse of the reaction on the previous slide. We have the same concentration values, so same temperature, same equilibrium conditions. And we're calculating Kc, but now calculating Kc for the reverse reaction. For the reverse reaction, Kc is still products over reactants, so it is now CO times concentration of H2O divided by concentration of CO2 times concentration of H2. This fraction for Kc, the expression for Kc, CO2 and H2 in the denominator, we go back a slide. This is the inverse of the Kc for this reaction. CO2 and H2 are in the numerator. So we could plug in all the concentration values and calculate Kc, or we can say that the Kc for the reverse reaction is 1 over Kc from the forward reaction, or I'll just write previous slide here. Because all that is changing between these Kc expressions is what's in the numerator and denominator. It's getting inverted, so we can invert that final value. So 1 over 6.25, which is 0.16. So here's the first way that we can manipulate a given K value. If you're reversing the reaction, then you take the inverse of the K value. I'll write that down here. Reversing a reaction equation yields the inverse equilibrium constant. Remember, for a reversible reaction, a reaction that reaches equilibrium, we can write the products on or for this reaction, we can write carbon monoxide and H2 on either side, but depending on what side they're on influences what Kc we're calculating. So given this Kc value, does the reaction lie to the left or the right? To the left. We have more reactants than we do products. So this reaction, with all 4 of these components present, will always have more CO2 and H2 present. The concentrations of those two will always be higher than CO and H2. So if we write the equation with those two as the reactants, then we have a small Kc. In the previous slide, they were written as products, so we have a large Kc. This way, the reaction lies to the right. The other way, the reaction lies to the left. But if you're, again, switching reactants and products, reversing the reaction, you inverse the equilibrium constant. Questions? Is that clear? Okay. Now we can also use a K value to find the concentration of a reactant. So here's another reaction equation. Bromine, gaseous BrCl, bromine chloride, decomposes into bromine and chlorine. So at equilibrium, we have partial pressures of Cl2, partial pressure of Br2. We have the Kp value, and we're looking for the partial pressure of BrCl. So first, we need to write out the Kp expression, and then we need to solve or rearrange to have partial pressure of BrCl as what we're solving for on one side of the equation. So first we need to relate partial pressures to Kp, and that's through this fraction. So Kp, pressure of products, divided by pressure of reactants, BrCl, the reactant, has a coefficient of 2, so we need to square the partial pressure. with me so far? Okay, but we need to calculate partial pressure of bromine chloride, BrCl. So we're going to rearrange the equation to have partial pressure of BrCl on one side and then everything else on the other. So I will be multiplying both sides by that denominator and then dividing by Kp. So that gives partial pressure of BrCl. It is still squared, equal to partial pressure of products divided by Kp. So I divided both sides by Kp. Plugging in all these values on the right side that we are provided and simplifying will give us the value of the partial pressure squared, but we need just the value of the partial pressure. So now we need to take the square root of both sides. That will cancel out this exponent, and then we'll get just the partial pressure. So partial pressure of BrCl, what we're looking for, is equal to the square root of that whole fraction, pressure of Br2, pressure of Cl2, divided by Kp. And now we can plug in values to solve for partial pressure. Okay, so I've plugged in partial pressure values, Kp value, divided, took the square root, and I get partial pressure of the reactant is 0.063. Do I have units here? An ATM, yes. So even though we don't have units for Kp, we have to think conceptually for these questions what the unit should be. We're talking about pressure of something, so that needs a pressure unit, and the pressures provided were an ATM. So that pressure should be ATM. For these equations, if you have like one pressure in atmospheres, one pressure in millimeter of mercury, of course you need to have the same units of pressure for this equation. And might as well stick with ATM, because if you ever need to use R, converting between Kc and Kp, your pressure should be in ATM, since R has units of ATM. So keep that in mind. All right, I'll let you pack up 1 minute early this time. We'll be done. Hey. Yeah. Yeah. Oh, yeah, I don't get everything because it's supposed to support them like through college. I don't know if there's anything else, but if you're interested in doing research, like in the department, are you about to graduate? Yeah. Okay. So oh, no. I know all of that. Okay. If you're interested in doing research, I'm sure there will be like opportunities through the department. Yeah. Yeah. No problem.